Hello, everyone. We are group 4, and our paper is on high-resolution image synthesis with latent diffusion models by Robert Rombach et al. And the presentation is by Ronald Campos, Mohammed Assad Haider, me, Sunit Bernani, and Stefan Werleman. So I first want to describe the details of the paper. It was presented at IEEE Conference for Computer Vision and Pattern Recognition in 2022, and it has over 372 citations. The relevant links to the paper and the code are provided in the slides. To give an introduction, the area of image generation in computer vision has been growing a lot. And right now we have two main models that we use for these tasks. The first one is GANs, otherwise known as generative models for image synthesis. And the next one is denoising models, otherwise known as diffusion models. So diffusion models are the more popular version for generating images because they're able to generate very high fidelity images, and they can also achieve a lot better variance than a generative model can. However, despite these benefits, it has one major flaw. The major flaw with standard diffusion models is they often spend a lot of computational power on fine-grained details that may or may not be perceptible to humans. Ideally, we could have a model that can generate high-fidelity images that train in a lower dimension in order to save computational power while also preserving as much detail and information as possible. As a real-world example, the paper says that a standard diffusion model can take 150 to 1,000 V100 days. In case you don't know, a V100 day is a day a model trains using a NVIDIA Tesla V100 GPU. So if you had one V100 GPU, it would take approximately, in the least complex case, 150 days to train. If you're coming from Google, it's about 2 Google TPU days for one V100 day. So in terms of speed, this is relatively slow. And it also requires a ton of computational power, which can basically put off a lot of researchers who don't have as much money or computational power to run these high-powered models. So I want to visualize the issue with a graph. So this graph is graphing the distortion, basically the quality of detail in the image compared to the rate in bits per dimension of a standard stable diffusion model or standard diffusion model trained on the Cypher 100 data set. So at the top here, when our distortion is really high at 80, this is when we have the least amount of detail. And at the bottom here, when it's 0, this is when we have the most amount of detail. So I first want to take a look at the left-hand side of this graph here. And here you can see that when our distortion is really high, from 30 to 80, you can see that our rate, our bits per dimension, is extremely low. So there's this very high range of high distortion data that is not getting very much processing at all by a standard diffusion model. However, on the other hand, when we're very close to the high detail, so below 20 to 0, when we have super high detail images, we're doing a lot of processing. And as we get extremely close to 0, we're doing the most amount of processing. So most of the processing happening in the stable diffusion model is being processed on details that may or may not be perceptible to most humans. So this basically can allow us to conclude that standard diffusion models waste a lot of time and energy on details that may not make a difference in the final output. So instead, we need a way to mitigate this issue. And I'll hand it over to Assad to describe the method in which latent diffusion models use to mitigate this.
Okay, is my screen visible?
Yes.
Okay, perfect. Let me get the pointer working properly. Okay, yeah, perfect. So we have seen that diffusion models operate in the pixel space, which means that they use raw images for training and inference. The problem with using raw images is that due to the high dimensionality of the pixel space, the computational overhead is very high. So what is the solution? We need to move from the pixel space to a lower dimensional latent space and apply the diffusion process in this space. To get the latent representation of the image, we use the autoencoder. The input to an autoencoder is the image, and the encoder compresses the image into a latent space representation of a lower dimensionality. The decoder reconstructs the image from the latent space representation, and the factor by which the dimensionality of the image is reduced is calculated by this formulation. And you will see moving on that the authors refer to different latent diffusion models by appending the compression factor to the name of the model. For example, LDM4, LDM8, which shows that the model is compressing the image information by a factor of 4 or 8 respectively. Okay, so for training the autoencoder, the loss function is this. This might look a bit complicated, but we will break it down into its components and try to understand each part. So the first part over here is the reconstruction loss. Next is the adversarial loss. And the last one is the regularization. First, let's touch upon the reconstruction loss. So the reconstruction loss is composed of two parts. The first is simply the pixel-wise difference between the reconstructed image and the ground truth. And it's calculated by either the L1 distance or the L2 distance. The second part is very important. It's the perceptual loss. So we need to understand why we need to use the perceptual loss in the first place. And the reason is that the L1 and L2 loss is not sufficient to ensure that the reconstructed image is semantically similar to the ground truth. So in order to ensure that the reconstructed image contains the features and the style of the ground truth, we need the perceptual loss. Okay, next we need to see how the perceptual loss works. And for this, we have this image which basically describes the whole process. On the left part of the image shows the autoencoder that we discussed previously. And the right part is a large convolutional neural network, usually a VGG16. And its function is represented by phi over here. And this large convolutional neural network has been pre-trained on a large data set like ImageNet. Okay, so next we know that the intermediate layers of the convolutional neural network capture the image features and style information very well. That is why we use the feature maps of the convolutional neural network that are produced when the reconstructed image represented by y hat over here from the autoencoder is passed through the CNN. And we compared those feature maps with the feature maps produced when the ground truth image is passed through this same CNN. And this comparison is summarized by this equation over here, which is basically, as you can see, phi, as I said earlier, it represents the function of the autoencoder, and we are just simply comparing the feature maps from the reconstructed image and the ground truth. So that was the perceptual loss. Next, we go on to the adversarial loss. Okay, this is the architecture of a patch-based generative adversarial network. It consists of a generator and a discriminator. At a high level, the generator produces images, and the discriminator classifies different regions of the image as either real or fake. The generator is trained to fool the discriminator into thinking that the generated images are real, and the discriminator is trained to correctly classify the real and fake images. In our case, in our model, the generator is the autoencoder that we have previously talked about, and the discriminator is a separate network. It's a convolutional neural network. Okay, so this was the part of the adversarial loss function that we saw earlier in the equation, and it is basically the discriminator's loss function, and it's the cross entropy loss between the discriminator's predictions and the ground truth labels. It is easier to understand what is going on if we rearrange the equation like this. Basically, take out the negative sign from this cross entropy loss. Now we can see that both of these terms, this one and this, are negative in the original autoencoder loss function. And the reason for this is that the better the discriminator gets at correctly distinguishing between real and generated images, its loss value decreases. Basically, loss value decreases. And therefore, the generator, which in our case, the autoencoder, has to do a better job to fool the discriminator. So that's why its loss value should increase. And that is why these values are being subtracted in the original autoencoder loss function.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Okay, and for the last part of that loss function that we saw, it is simply the regularization. Yeah, it's used. It's basically the regularization is used in the formulation in order to reduce the variance of the latent space, leading to more stable training and predictions. The authors use two different types of regularization. First is the Kullback-Leibler regularization, which is a measure of how similar two distributions are. And in the case of the model, this was used to penalize the model for having a latent space that is too far from the prior distribution, which is chosen as the normal distribution with zero mean and unit variance. The second regularization that the authors used was the vector quantization regularization, which transforms the latent space into a discrete space. And this is done by replacing the encoded latent representation of the image by its nearest neighbor from a discrete space codebook. Okay, that was a very in-depth discussion about the autoencoder, but how does it affect the diffusion process? This was the objective function of the normal diffusion model. The only change in the objective function of the diffusion model is now that the image represented by X over here is replaced by its latent representation over here. And the benefits of this approach are that, first of all, as discussed before, it's efficient. Secondly, it is able to provide a better semantic representation of the image by filtering away unnecessary details. And another plus point is you only need to train the autoencoder once. Then we can use it for a variety of tasks like in-painting, super resolution, etc. We'll now look at how conditioning is incorporated in the latent diffusion model. So this was the autoencoder that we've discussed in detail. This is the conditioning input of the network. We can condition the diffusion model with a variety of inputs like images, text, and audio. And these inputs are transformed to a standard dimension, a standard size, usually via a transformer-based network. Okay, and this here is the latent diffusion model operating in the latent space of the encoder. Okay, and the conditioning input from the previous step is used to influence the diffusion process via cross-attention layers inside the unit. As we know, the attention mechanism is composed of Curie matrix, the key matrix, and the value matrix. And the Curie matrix is calculated using the feature maps of the unit, while the key and value matrices are calculated using the features from the conditioning input. Finally, attention is calculated using this formulation that we have seen previously. Now I'll hand over to Stefan to discuss the experiments.
Thank you, Assad. So in this section, we're going to go over the 4 experiments that were conducted to basically evaluate and evaluate the performance of the LDMs. The first 3 will be covered by me, and the last one will be covered by Ron later. Here is some of the data sets that will be used throughout these experiments. Now, before moving on, we need to determine the best 2 models to use for the experiments. And so far, we have 6 LDM models with different downsampling factors. Note that LDM1 is the pixel-based model. And for this graph right here to record the FIDs, we ran a total of 2 million training steps here. And although all 6 of them have generally minimized their FID score, the best 2 LDMs are 4 and 8, as you can see here. And then furthermore, we want to check the inception score for these LDM models as well. At the very top, again, over 2 million training steps as well. LDMs 4 and 8 still achieve the highest inception score here. And finally, we want to compare the LDM's sampling speed with different numbers of denoising steps. This graph right here, these results were produced by the Celeb HQ dataset. And you can see here how LDMs 4 and 8 were able to maintain a relatively low FID score while steadily increasing the sampling throughput. So this is a more of a healthy projection compared to the rest of them. So which means that LDMs 4 and 8 will be used throughout the next 4 experiments to maximize the results. So the first experiment is image generation with the unconditional versions of the latent diffusion models. And the metrics used for this are FID, precision, and recall. And the hyperparameters set are the factors of 4 and 8, regularizing the latent space to 64 by 64 with 3 channels, and the learning codebook of 8,192. There are more hyperparameters set for these models, but these bottom 2 here are the shared amongst all the other LDM models that will be used here. Luckily, the LDM 4 produced a new state-of-the-art FID of 5.11 for the Celeb HQ dataset. State-of-the-art meaning that no other model within this dataset has produced an FID score of 5.11. And LDM 4 and 8 outperformed the other GAN models in terms of precision and recall for the FFHQ and Lausanne Churches datasets. However, the style GAN and projected GAN models outperform LDM4 for the Lausanne bedrooms with all 3 metrics. The next experiment tests the conditional LDM for text-to-image synthesis. And the results was that the LDM8, or the guided version of LDM8, produced the best inception score compared to the AR and GAN methods. And it was able to do that because it was trained as a KL regularized LDM, KL meaning Klober-Leibler, and it also used the BERT tokenizer for language processing. We also improved training performance by running 250 DDIM steps for both the conditional and unconditional LDM, where DDIM stands for the denoising diffusion implicit models, which is commonly used to accelerate sampling, which then in turn improves overall training performance. And so here are some examples that the LDM model has produced. So this first one here, you have a street sign that reads latent diffusion, produces 2 images with the same text. You have a zombie Picasso, and you get the point with the rest of these examples here. Furthermore, here are more examples of what the LDM4 produces. As you can see, after it tokenizes the key words from the text, it was able to segment some of the objects in the images here. So you have the traffic light, and notice that in all 4 images, the traffic lights are relatively in the same position. Similar here with the trains, they're relatively in the same position. And according to this visual here, you can see how it's segmented onto that position. And same thing with the vase here. Another cool thing you can use with this conditional latent diffusion model is generalize it so that it samples images beyond the 256 by 256 resolution. So this image here has a resolution of 512 by 1024, which is pretty neat. The next experiment is super resolution, and we want to compare the LDM model with 2 other models that were commonly used for super resolution. And so good news, the LDM SR model that they that they used produced the best FID score. This was possible because the model was conditioned with low resolution images via concatenation during training. And so here are 3 models. You can see here in the very center, the LDM SR. However, the SR3 model produced more coherent images. And you could tell here, if you look at the wheel of this wagon, there is some missing detail in this image. Well, compared to the SR3 model, it looks a little bit more complete. But in general, you can still efficiently use the LDM SR in terms of training and still produce a pretty good quality image for this case. And so now I'm going to pass it on to Ron, where he'll talk about in-painting.
All right. So the last set of experiments that were conducted were regarding in-painting. As we know, in-painting is where we take an image and we fill certain regions of that image with new content. And this is done either to fix a corrupted image or to replace a part of an image with something else. These LDMs, they followed the same protocols as a model called Lemma, which at the time was the state of the art for in-painting. Some of these protocols or performance metrics that were used were FID scores, throughput, which we just covered with Safan, and LPIPs, which is a metric that's used to gauge the perceptual similarity between 2 images. Now, this is actually a very interesting metric because it's been shown to relate really well with human perception.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Here are some of the results from the model. As we see, all of the objects are completely removed and the backgrounds are filled in quite nicely. And some of these experiments that were conducted were, they created 4 LDMs, which were trained on 215 million parameters, and they used the places dataset for this. The first LDM just had a downsampling scale factor of 1, so this is akin to just a pixel-based diffusion model. And then the next 3 LDMs, they had a scale of 4 for the downsampling with just different hyperparameters. So one had a KL reg, the other 2 had VQ regs, one without attention, one with attention. What they found from these experiments was that LDM4 performed at least 2.7 times faster than LDM1 and had a better FID score by at least 1.6 times. The throughput also notably outperformed LDM1 across all the models. So inspiration was taken from these experiments, and the authors decided to create a big LDM4 with a VQ reg without attention, and this was trained on 387 million parameters. They found that it worked really well for images with dimensions of 256 squared, but that for images that were 512 squared, there needed to be some small adjustments to be made. What they did is they fine-tuned the model for half an epoch, and they found that this allowed the model to adjust well to feature statistics, and not only that, but actually set a state-of-the-art FID score. So they set a state-of-the-art FID scores for both images that were 40 to 50% masked and across all samples. As far as the perceptual similarity scores, they are beaten by Lemma, but the differences between the models are very negligible. If you notice, it's only a difference of 0.003. So we actually conducted our own experiments for text-to-image generation. And to do this, we just followed the instructions that were located in the README of the repo. The model that they provide has a fixed set of hyperparameters. So they have an LDM8 with a KL reg, and this actually happens to be the best performing model for text-to-image synthesis. So if you're interested in doing this, you can just use the script right here, replace this with your desired prompt, choose your preferred image style. You could choose something like oil on canvas. This right here is your number of samples, which denotes the number of images that you'd like to generate per row. The number of iters does the same, but for columns. H and W control your dimensions. And then DDIM ETA, scale, and DDIM steps. These are the parameters that actually control your generations. So this ETA parameter controls the diversity of your image generations. Scale does that for the quality of the image. and steps controls the speed at which these images are sampled. So there's actually a trade-off between these three, and this is actually based on the concept which was covered in the GLIDE paper. The model uses a classifier free guidance as shown by this equation, where S is represented by the scale parameter. So the trade-off is that you can increase the scale, but at the cost of the diversity, which is the ETA. Conversely, you can increase the diversity, but the scale, the quality might get affected. So we actually attempted increasing these both, and we found that if we increased both to an order that was too high, then that the image generation would occur, but we'd receive a runtime warning, and the actual generation would just actually be a completely black image. So after inputting this script, you'll get a prompt that resembles something like this. They'll give you a progress bar, which shows you how fast your image is being generated. Approximately, the images took around somewhere between 30 seconds to a minute and a half, depending on what your parameters were to generate. And here are some of our generations. So this prompt that we input was a dog putting out a fire. As we can see, we have different parameters here, different styles and scale factors that we use. And we can notice that this S actually denotes the scale factors. So if we notice when these two, when compared to this image right here, which has a scale of 35, they kind of fall short in terms of quality. This one seems like it's a little better generated, right? So we did the same with another prompt called a person crossing a busy intersection, and we can note the same. So this image right here, we could see that there's people present. There's what looks like to be cars and roads, but the people don't really appear to be like heading in any direction, right? And everything just kind of seems to be just placed there. Whereas with this image, where the scale factor is of 35, this person appears to be headed towards the intersection. Here's the last set of images that we generated. And so in conclusion, a good way to sum up LDMs is that they're essentially diffusion models that operate on the latent space of an image. They can significantly improve both the training and sampling efficiency of the noise and diffusion models. And the authors of the paper did a good job in showing that they fare well when compared to other state-of-the-art methods, all which have been shown. Some points against or for the paper, are the latent diffusion models. They achieve a much lower training costs and faster inference speeds when compared to standard diffusion models. Their architectures are very flexible. They work on many tasks. And the biggest point to note is, as Dr. Shaw said, so this is actually the predecessor to stable diffusion models. So this paper proposed a new perspective for interpreting and working with the features from the latent space of an autoencoder. And like I just mentioned, it is the backbone to stable diffusion, which, as we know, is the state of the art in this realm. Something else we wanted to know is that all of the code is open source, which is just great for the spread of knowledge in the community. Some points against the paper. One drawback to this architecture is that its use might be questionable for a task like super resolution, where fine grain accuracy is required, right? Stefan just showed this where SR3 produces a slightly better image reconstruction versus LDM SR. So if you're really looking for the best model for a task like super resolution, another approach might be preferred. Another point against the paper is that it doesn't really explore to what extent the model is misrepresenting some of the data that it sees. So I know this is a problem with diffusion models in general, but this is especially true with latent diffusion models because they are essentially a two-step process. So let me backtrack a little. Diffusion models, they do have a better coverage of data distributions versus, say, a GAN-based approach. But in general, some of the data that they might see might not be characterized correctly. This is something that the authors acknowledge, that it is an important ongoing research question, but it's not something that's really addressed beyond that. So the last point against the paper is the fact that it doesn't really experiment with adding objects to otherwise unaltered images for inpainting. So we can go back again to the GLIDE paper. If we consider that paper, There, they combine the restorative properties of inpainting with text-to-image generation. We feel that that sort of experimentation would have been nice to see. And that sums up our presentation. Thank you for listening.